Good morning, everyone. It's my pleasure to be with you today. But if there's one thing that always makes me nervous when giving a talk, it's to be the last speaker to speak just before lunch. So I'll try to keep it as engaging as possible. And hopefully that should be easy because I feel very passionate about the problem and the topic I'm going to present today. So if you are attending this conference, chances are you do love working with big data and you work with big data on a daily basis. But in fact, I believe that you probably are more likely to have a love-hate relationship with the data that you work with. And this is the topic we're going to discuss today. So this topic of love-hate relationship to our data is something that has followed me throughout my entire career. And so I remember when I started as a machine learning scientist, at first I was very frustrated because usually the companies I was working for did not have enough data. And suddenly, when we saw this huge boom of large data sets everywhere, I started complaining about not knowing what to do with it. And later on, when I became a manager, I constantly had to manage budgets and figure out ways for my teams to basically manage to do machine learning with big data. And I felt so passionate about trying to provide a solution to the community that at first I joined one of the largest labeling companies, Figure 8, as their VP of machine learning. And I eventually started my own company, Alectio, to basically try to provide solutions to the problems associated to doing machine learning with big data. So just a few words about Alectio. So we're still a very young company. You probably haven't heard of us. And we're currently 13 people, less than 2 years old. And everything we do is essentially to help machine learning teams and machine learning companies do machine learning in the edge of big data. Right? And just like the rest of you guys, we believe that machine learning is awesome. There is no question that we've done a lot of progress recently. But there is also no question that doing machine learning with big data is expensive and time consuming. Right? So the way we sort of try to solve those challenges associated to doing machine learning with big data is essentially by trying to provide solutions to help people reduce the amount of data that's actually necessary to train machine learning models. And by doing so, we hope to help people reduce training time and essentially time to market. We help people reduce operational costs, whether those costs are associated to data labeling, compute, or storage. And in fact, our crazy hope is even that we potentially believe, and we've seen cases where training a machine learning model with less data has actually helped companies achieve better performance just because you're solving a garbage in, garbage out problem. But before we talk about how it's possible to do machine learning with less data and achieve similar results that you would have with large data sets, I would like to try to make the case why I believe it's time for the community to have a paradigm shift in this direction. And so the very first thing I'd like to discuss is basically the history of big data. And when I discuss the history of big data, I usually like to start with the history of deep learning because I believe these two are so closely tied to each other. Right? Something that very few people, even experts in the field, do realize is that the mathematical framework and the early version of our modern neural nets have actually been around for a very, very long time. In fact, like 70 years, essentially. And even the modern version of the math behind backpropagation and our neural networks have been around for decades, right? But as we all know, it took decades, and it's only in the last 10 years that we essentially started seeing like a true usage and practical applications for deep learning, right? I mean, so why did it take so long, right? So even though backprop was invented in 1975, it took 15 years or almost 15 years for Yann LeCun to be able to practically test backpropagation. And then it essentially took another like 20 years to reach the point where we started seeing an explosion of people using deep learning on a daily basis, right? So what happened there, right? So Of course, there's no question that this is essentially associated to the coming of the big data era, which is tightly coupled and associated to an era where we started having better hardware, right? I mean, so it's unclear whether we got better hardware because there was a need for more data, or if we got more data because suddenly better hardware became possible, but these two are tightly coupled to each other, right? So it seems that now there is no limits anymore to what we can try to achieve, and we can finally put in application all of this research we've done for such a long time, right? So the problem, though, is that doing machine learning with big data is actually very challenging for many different reasons, right? So when you work with big data, essentially, like the more data you have, the more data labeling you're gonna have to do, right? It does not necessarily seem to be a big problem, specifically if you're not in charge of a labeling budget. It does not, maybe you don't realize that this is a problem for your company, but a lot of the labeling today tends to be done manually. And so that tends to like incur costs for the company. It's difficult to manage and it takes time, right? Even data storage, which doesn't seem to be such a big problem because typically data storage isn't the most expensive part of doing machine learning. We all know that S3 instances are significantly cheaper than an EC2 instance, but still for many companies, like given the volume of data that they collect, it might eventually become a problem. And so even though we're light years from the age of the floppy disks, this can still be an issue for many companies. Then there is the problem of compute. So that's something that even ICs probably can be more familiar with. When you train a machine learning model, and if this deep learning, like for example, you work with a deep learning model which is extremely deep or complicated, basically training this model either on your own servers or on the cloud might be very expensive. In fact, I wouldn't be surprised if your manager has been complaining about the costs that this has caused to the team. And then eventually, like even if you forget like the monetary aspect of things, working with larger data sets obviously tends to make the entire process a lot slower, either when you think about data preparation or when you think about the training process itself. So, I mean, at this point, I'm pretty sure a lot of people will feel like there is an easy solution to this problem. And that solution is to get better hardware, right? I mean, and so to some extent, it does make sense because with better hardware, we got to where we are today, right? So this is essentially what Moore's law is promising us. Moore's law is this empirical law that states that the performance of the hardware that we create will keep increasing proportionally, basically at the same speed than the data that we collect, right? And that actually makes sense because we need better hardware also to collect more data, right? The problem, though, that some people will point out, and some more and more experts actually tend to believe in, is that to get better, faster, like higher performance hardware, you need to get smaller transistors, right? And the problem at some point is like the size and the scale of the transistors we're reaching at this point is putting us in a situation where that scale is reaching the scales where the basically like scales governed by the law of quantum physics, right? I mean, so in other terms, there is a chance that we won't be able to do any more significant progress with hardware unless we start mastering quantum computing. And I don't necessarily think we're there yet, right? So even though for many years, many people tend to see what I call the optimistic view of Moore's law, if you are being honest with yourself, you probably believe that there might be some slowdown right now, right? So now, whether or not you agree with this conclusion and you agree that there may be like some slowdown in Moore's law, you also have to admit that even if better hardware exists, it's not necessarily always available to the common machine learning scientist out there, right? And so the fact that good technology exists doesn't mean that it can practically be used by the various machine learning companies out there. Now, something that I feel, unfortunately, is not being talked about enough is the environmental aspect of big data, right? So if you're going to work with more data and better hardware, you still have to keep in mind that this hardware functions on electricity, right? I mean, so just to make a point, I would like to give you a few numbers about data centers, right? So as of 2020, we now have 40,000 zettabytes of data collected worldwide. If you think about this number, that's basically 40,000 billion of gigabytes. That's obviously a very, very large number, right? And you need to put this data somewhere. So typically you'd put this data in one of the many hyperscale data centers somewhere in the world. And these are actually very large consumer of electricity, of power, right? And I mean, depending on the source that this data and those numbers come from, like the average is basically like people estimate that 2% of all power consumption on planet Earth actually come from big data. So the reason why this is happening is that those data centers are typically not very efficient. So it's basically like one of the reasons why this is happening is that you don't only need to make those machines function, but you also have to cool them. And so if you have an AC at home, you know how expensive a cooling system might be, right? And unfortunately, many of these hyperscale data centers tend to be in places that are not particularly cold. And so since we've talked about the impact on the power grid and obviously on our electricity bills as machine learning scientists, or the electricity bills for our companies, I think it's worth talking about carbon emissions as well. So right now, about 2% of all human-generated emissions come from big data and data centers specifically, right? It does not seem like a lot, certainly compared to other industries like the clothing industry or agriculture, for example. But what's sort of like really concerning here is that we see this uptrend. Like, for example, we predict that by 2025, just like 5 years from now, we'll reach like 5.5% of all generated emissions. And this is sort of the opposite trend that you see with other industries. We're one of the very few industries, in fact, that is not working hard to try to reduce this number. And when I first saw this number, my hope, of course, was that we could adopt more solar electricity and be more sustainable. But unfortunately, if you look the numbers here, this is actually not the case. So before basically jumping to the next session and discussing how it's possible for anyone to try to control the amount of data that they work with, I would like to close this argument and try to finalize the case for smaller data sets by sharing with you a few numbers. Did you know, for instance, that 55% of a company's data was typically what you would call dark data? So dark data is essentially data that even it exists, but the company either doesn't know how to get to it and they don't know how to access it, or they might not even know it exists in the first place. In fact, 85% of all data is either dark or ROT, which is essentially an acronym for redundant, obsolete, or trivial data. Just think about this number. 85% of the data that we have stored somewhere is actually not something that you can use, right? And 90% of all unstructured data is never even used either for analytics or for machine learning purposes, right? I mean, so now, again, when I saw this number, my hope was that maybe in the future, when companies get in possession of better servers and so forth and so on, maybe they will leverage the data. Unfortunately, for us, it turns out that 60% of all data we collect loses its value immediately when collected. So essentially, 60% of this data cannot even be used at all. So this should basically prove you something very important. We're all data hoarders. The machine learning community and the data community is hoarding data that it cannot even be used eventually, right? So this sounds like a terrible statement to make, right? But when I look at this as being an opportunity, because this should prove to you that there is a lot of room for improvement. So at this point, I hope that you're sort of convinced that scaling down is the way to go, and that it's time for all of us to shift our opinion about big data being necessary for good machine learning models. So this is sort of like weird for us to say, because of course we've all been trained and to believe that the more data, the better our machine learning algorithms would perform, right? And I've been taught that. I'm sure you've been taught that as well. The good news is that there is actually a lot of hope, and there is a lot of research in many areas that are sort of like either try to control the cost associated to working with big data, or to try to control the actual amount of data that we work with altogether. For example, if you just focus on data labeling cost, you not only have like new breeds of machine learning algorithm that help us like automatically label data. For example, you might have heard of the human in the loop paradigm that helps you like identify poorly labeled data, or leverage automated processes on top of humans. Essentially, humans just focus on the corner cases. You might have heard of the snorkel algorithm, which is using weak supervision to automatically label data. But like for me, like the biggest promise is going to come from other learning paradigms such as transfer learning, meta learning, and active learning, which all attempt to try to reduce the amount of data that we train our machine learning models on, right? So now, of course, none of these methods, and there are many I didn't list here, can solve all of our problems at once. But there is a lot of promise in a lot of different areas. Now, of course, I'm sure you won't prove that you can actually train a model with less data. So this is basically just like a couple of screenshots that were taken from one of our blogs, one of our blog posts. And that's basically some research we've done on an open source data set called DeepWeeds. And the problem is essentially image classification for weeds, right? And the plot that you see on the right here is basically a series of violin plots where we try to see how models perform, or how a model performs when you vary the amount of data that it's trained with, right? So each one of these violins here are essentially showing the distribution of the performance of the same model being trained on 20 different models, or 20 different data sets, excuse me, trained with the same amount of data. So the first violin plot that you see here is essentially the distribution of 20 experiments that were all trained examples of like in each one of these cases, the training data set was a sample of 20% of the entire data set. And what we displayed here is the accuracy that was measured on the set for each one of these experiments, right? And so we repeated the same experiment for various amounts of data, right? And there are actually two very important conclusions here, right? If you realize that the very best sample of size 20% actually overperforms the worst samples of size 80%, right? So it should prove to you two very important things. First and foremost, it matters which part of the data you train with, right? Because like, for example, even when you pick 80% of the data, there is a huge variance in the accuracy of the data that you're going to work with, right? And this is all just like random data and samples that were randomly picked, right? Number two, you should see that it's possible to get a better model with less data, just because like there are many configurations where the best performance of like even for 40%, 20%, 60%, the best one all overperforms a large majority or a large fraction of the cases where we trained on 80% of the data, right? So now that you believe that, and hopefully you do believe that it's possible to train models with less data, I would like to explain a little bit deeper how active learning works, and because active learning is at the very root of a lot of things that we do at Alectio, right? So you probably heard about active learning, but chances are you haven't heard the right definition, because I believe that active learning is one of the concepts that is the most misunderstood in the industry. So the definition, the actual definition of active learning is that active learning is a semi-supervised learning technique based on an incremental learning approach that typically people are going to use to reduce their labeling costs. So what does it mean? It means that because it's semi-supervised, we work with only partially labeled data. The fact that it's incremental means you're gonna retrain with by adding more and more data, and we basically process in loops. So each loop is a process where you train your model with a subset of the data. I'm gonna show you how it works later. And typically people have been using this mostly for operational reasons. Up to now, there's been very little research in trying to use active learning to try to get better models, right? And so even though it's kind of difficult to put in application and in practice in real life, the process of active learning is actually fairly simple. It's a repeated set of loops where you select data, you label this data, you train with this data, and you run inference with this data. So I'll show you what the pseudocode looks like so that you can try and implement this for yourself. I just want to emphasize that active learning has nothing to do with with auto labeling, and it has nothing to do with human in the loop, even though a lot of people tend to believe that. All right, so what are the pros and cons of active learning? Well, first and foremost, because active learning was originally designed to help people save on labeling, of course, this is like one of the major pros of the technology and the paradigm, right? Active learning is also doing a lot better than any other semi-supervised learning techniques when it comes to like generating biases. In fact, it's a lot more difficult to generate biases with active learning than it would be with a regular semi-supervised learning technique, which you might have used or heard of elsewhere. And finally, like from my perspective, I see active learning as being one of the very first steps towards like becoming more pragmatic when trying to do machine learning. Unfortunately, active learning has a lot of downsides as well, and you'll see why when I show you essentially how the algorithm works. First and foremost, it tends to increase training time. It tends to increase compute costs because you have to retrain the model over and over again. And it's actually pretty difficult to put in application, certainly more so with data sets that are messy like they are in the industry. So even though you tend to see a lot of research in academia, not a lot of people are using it in the industry. So the good news is that there is a lot of it's fairly easy to put, or it's fairly easy to understand how it works. So I'm going to try to explain how this works now, right? So when you do active learning, you essentially start with the same training data set you would work with if you were doing supervised learning, right? You're gonna work with the same model. Typically, you already have a model that's optimized, and one of the most common application for active learning is to retrain a model that's already been optimized. And you're gonna have a similar data set, just like the same way you would have for supervised learning, right? Now, within your training data set, you're gonna split your data into the unlabeled part of this data set and the labeled part of this data set. That's essentially one of the only difference at this point, right? So what you're going to do is, like, as I said earlier, the process starts with a select process. So at first, typically people tend to randomly pick some of the data. Then this data gets labeled. It gets labeled you can label it whichever way you like. Then you're going to send this to your model, essentially train your model and get a model instance with this specific subset of the data. Now, because you've used a small part of your data set, you shouldn't have any expectations that this model is going to perform really well. In fact, probably it won't, right? And then once you're done, you basically put the data which you just labeled and just used to train your first version of a model into the batch of data that you call the labeled data set, right? And then this is where things get interesting. At this point, you're going to evaluate how good your model is on your test set. And simultaneously, you're going to run inferences to basically try to probe the model to see where the model is at, right? And so you're going to basically get a lot of predictions from the unlabeled part of your training data set, but you cannot use those predictions per se to make a decision. For example, you cannot say that because your model seems to be underperforming on cats, for example, you should pick more cats within your training data set, because if your model is struggling with cats, the data that was predicted as a cat is actually very unlikely to actually be a cat, right? I mean, and so the fact that you are not relying on the prediction itself is the very reason why it's unlikely that you will generate biases. It's more unlikely that you will generate biases compared to other semi-supervised learning techniques, right? And so then you keep going, you increment the loop number, right? I mean, so we went through the first loop, and now we're going to do the second loop, where we're going to select additional data. And this is where you can be smarter about selecting the data, because you know more about where the model stands. And you're going to label the subset of the data, which means you're going to have to do labeling incrementally. And then you're going to retrain your model, not only with the data which you've just selected, but also with the data which was already labeled previously. And this is actually one of the reasons why active learning in its original format tends to be very compute greedy, because you keep retraining on the same data over and over again, right? So now let's jump into the pseudocode. So the pseudocode is actually fairly easy to understand. And once you'll understand how the essentials work, you're going to be able to start experimenting with it yourself. And I sure hope that you try to do that. So when you initialize the process, you will basically initialize your unlabeled data set to the data, because the assumption is that you start without any labels in your data set at all. And then you're going to jump into the first loop. For the first loop, usually what you do is, like, when you select the first subset of the data, you tend to do that randomly, because you don't know much about which data is actually going to be useful to the model. And then you're going to label this data. How that data gets labeled does not matter. It can be done manually. It can be done with a human in the loop process. It can be done with machine learning alone, right? And so the reason why I mentioned earlier that active learning per se is not a human in the loop process is that you could actually use a fully automated process to label this data. In fact, you could use something like Snorkel. And in this case, there would not be a human in the process or a human involved in the process at all. Then, quite obviously, so since you label some of your data, you're going to have less data to unlabel or less data to pick from in the next loop. You're going to train your model with the data you just selected. And then you're going to run your inferences. And basically, so this is where it gets interesting, because this inference step is essentially the point where it is your opportunity to try to measure where the model is struggling and try to help the model get better. So usually what people do at this point is to try to identify or measure the level of uncertainty of the model. And a lot of people do that by using a confidence strategy, or a querying strategy called confidence, as we're going to talk about later. Right? So you keep going over, but like what gets interesting for the next loop is like now you can use the inference data to try to be smart about which data you should pick. And so this selection function here is what people refer to when they speak about a querying strategy in an active learning process. So now the question is like, how do you tune an active learning process? How do you know how many loops you need to use? Well, it's difficult to predict ahead of time. And usually people pick a number of loops based on operational constraints, such as a specific amount of time or a specific amount of money that they have to spend on data labeling. How large should the loops be? Well, that's another hyperparameter. Usually when people do regular active learning, they tend to control or set a loop size ahead of time, but there's actually no reason why this number should be fixed, why this number should be constant, and why this number should actually be decided for in advance, right? I mean, so in other terms, that's a parameter that can be tuned as you go through the active learning process. And so this is one of the space where I believe there is a ton of research that needs to be done, right? Finally, maybe like the most important question here is like, what do you pick for a querying strategy? So the most common thing that people are going to do is to try to measure the uncertainty of the model. You'll measure uncertainty by looking at the prediction, the confidence level with which a prediction is made. So even though you cannot look at the prediction itself, you can try to see how confident the model is. Unfortunately, predicting uncertainty is very difficult, specifically with deep learning models. So traditionally, those querying strategies tend to be static functions. In other terms, you're using the same sampling technique over and over again, but you can actually become very creative. You can try to have something that would change over time. It does not need to be decided ahead of time. The only constraint for you is really to identify, like the only thing that a querying strategy is technically, it's simply a sampling method. So just to show you a few results, like these are like again, going back to deep weeds, like these are a couple querying strategies that we work with. And so one thing you can see right away is that not all querying strategies are going to be equally good, right? Which sort of like reflects what I said earlier, that the subset of the data you're going to pick sort of matters a lot, right? Here, in this case, the most standard querying strategy that everybody uses, which is low confidence, actually performs very poorly. In fact, it performs worse than randomly picking the data. Just think about this, right? And so we actually obviously do a lot of research in this space. And one of our proprietary technology is what we call auto-active learning, which is a process where you do some of the things I mentioned earlier. You use like a non-static amounts of data or basically querying strategies. And you can see that without doing any tuning at all, we're able to achieve the same performance for 80% of the data that the margin querying strategy did, right? I mean, so of course, margin is performing pretty well. The problem is that if you do not know which querying strategy is going to work, you would have to essentially bootstrap and brute force a lot of querying strategy to get to that level, right? I mean, so there's obviously a lot of research to do there. So I seriously encourage everybody to start looking into active learning, because active learning shows a lot of promise, not only to try to reduce the amount of data and reduce cost, but also in terms of many different things, right? So what we're trying to do and what we do a lot of research on is basically building a better breed of active learning. So what does this mean, right? First and foremost, it means building something that's more robust. One of the problems of active learning is that it assumes that all data is correct, right? I mean, so like active learning is trying to identify the most useful data within a data set, but this assumes that no data can cause harm to the model, which is usually not the case when you work with very messy data. We also believe that it's time for the industry to start adopting machine learning-driven querying strategy. The traditional querying strategies typically are preset, predetermined rules based on, it's essentially a rules-based sampling method. And there's actually no reason not to do this. In fact, just the same way that eventually at some point people decided to use machine learning as opposed to rules-based models, it's time for us to adopt machine learning-driven querying strategies. I also believe it's time for us to realize that active learning is actually very promising in different areas as well. For example, by trying to analyze which data was prioritized by the system, you can try to understand which data was the most useful, and you can try to start diagnosing why this data was more useful and maybe collect more of the same data, identify the weaknesses of the model, and so forth and so on. Finally, you might remember that I mentioned that active learning tends to be very compute expensive. And so one of the things that we're extremely focused on these days is to try to create a version of active learning that doesn't increase the amount of compute being used to train machine learning models, right? I mean, so you can do this by figuring out when you need to stop. Active learning tends to lead to these plateaus or plateauing learning curves, and basically there is a point in time where it seems that the model isn't learning anything anymore. So the sooner you identify when this happens, the better. And we're also trying to find ways to avoid to retrain on the entire set of selected data and essentially only train on the data that just got selected. So my conclusions today is that I think it's high time for the machine learning community for a shift in paradigm, right? I think people need to realize that less can be more even when it comes to data. I obviously believe that big data is amazing, but I believe big data is amazing because we now have the opportunity to become more picky about the data that we use, right? And the good news is that it seems to me that awareness, generally speaking, is starting to raise. There is more and more research in this space. In fact, like there was never as many papers on this space on active learning and on the many other concepts we talked about earlier than there was in 2019. Active learning is obviously very promising. There is a lot of promise in using active learning in the industry as well. And it can be used beyond the use case of trying to reduce the amount of data, the amount of money spent on data labeling. The problem, though, is doing active learning is extremely challenging. As you could have seen from my presentation, vanilla active learning is really hard to use with messy data. So that's one of the things we're trying to do a lot of research on. And doing hyperparameter tuning is difficult and time consuming. Regardless of all of this, I hope all of you enjoyed the presentation, and I hope you'll be interested in trying to validate or test active learning on your own use cases. We'd love to hear about how this goes. We'd love to help. And I also want to encourage everybody to visit our blog post. We publish case studies all the time. We talk a lot about our technology. So I hope you enjoyed the presentation, and I hope you'd be interested in hearing more about active learning in general. Thank you.